Hiya! So in today's video, we're going to be talking about Chebychev's inequality. So remember how we kind of had this, how when we're talking about standard deviation, we're thinking about how much this stretches our distribution, how stretched it kind of is. So it turns out that that the standard deviation limits the expected value, or that the probability and the expected value can only differ by so much based on the standard deviation. And this is known as Chebychev's inequality. And so let me highlight that, Chebychev's inequality. And so what this is basically stating that the probability of the difference between x and the expected value, so whatever the distance is that this is greater than k standard deviations of x. This is going to be less than 1 over k squared. So in other words, the probability that you're far away from the expected value is less and less and less. This is really this idea of the bell curve, in that most of the things should be in the middle and everything else should be on the right, on the like less things should be on the out. So what we're saying is most things are here. And that's basically what this is saying. So we're just gonna jump in right away and look at an example. So what we're doing is we're working at a financial company today. And here we're looking at all the transactions of all your customers. So you got a ton of transactions, and you want to double check that everything's okay. So you notice that you've had 1 billion transactions. So like there's a lot of transactions. So you have 1 billion transactions. And the average transaction is roughly $20. So this right away, I should know that average tells me that the expected value of x is equal to $20. So we know that right away. And then what else? And if we square the values of the transactions, the average becomes 404. So squaring the value of the transactions, the average becomes 404. What this is saying is our x squared is 404. So e of x squared, right? We're squaring the values. The expected value is 404. And it's asking find an upper bound on how many transactions are over $50. So we're looking at 1 billion transactions. How many of them are above $50? Like at most, how many are above $50? So we let x obviously be the transactions, equal value of transactions. And what we get is, so let's first calculate our variance, because we also need to, so to use Chebychev, we have e of x, but we need SD of x. So let's calculate variance of x. This is e of x squared minus e of x squared. So we get 404 minus 20 squared, which is 404 minus 400, which is 4. And it should always be positive, so we're good. What this tells me then is that the standard deviation is the square root of 4, which is just 2. Okay, so we got the standard deviation. Nice and easy. Now let's calculate the probability that a transaction is greater than or equal to 50. Okay, so here we're going to use a very similar thing as before. We're going to standardize. So to standardize, what we do is we just add and subtract the expected value, etc. So we have x minus e of x over SD of x is greater than or equal to 50 minus e of x over SD of x. So far, so good. But the thing we're going to try to remember is what we're trying to do. What we're trying to do is come up with some formula like this. So maybe what I'll do is let me quickly copy this. Is it's gonna let me? Oh, but it won't let. I can't paste it, so it won't matter. So let me do this. Let's see, it won't let me paste. Anyway, I'm going to rewrite this idea here on the side so we keep track of what we're trying to do. The formula we're trying to get is inside the probability, we want x minus e of x greater than or equal to, or greater than k. I guess the equal doesn't really matter too much. Greater than or equal to sd of x. So this is kind of what we're trying to come up with. So we have the x minus e to the x part, right? And so what we really want is this sd on the other side. So let me take this sd and move it to the other side. So we get x, the e to the x is 20, right? So I'll do, I'll just keep them e to the x for now. E of x greater than 50 minus e of x over sd of x. And I'm going to keep the sd of x here on this side just so that I can keep this value here. Okay, so what do we have? Let's plug in some numbers. So we have minus 20 greater than 50 minus 20 over the standard deviation was 2. And this one we will keep here because I really want to emphasize this sd of x for now. So here we have the probability that x minus 20 is greater than or equal to, so here we have 30 divided by 2, which is 15, sd of x. And then notice here, this is going to be less than or equal to, if I take the average, the absolute value of 20 here, right? This is kind of a little thing to note, because x could be less, or it could be, yeah, less than 20, and which case we would have a negative number, and we always want the positive. So we're going to be taking, that's going to increase our probability potentially. We don't actually know. And so we need, this is always going to be less than. And we have 15 of sd of x. Now here, this is where we can finally use Chebychev. So this by Chebychev we know this is less than or equal to 1 over, we take our 15 and we square it. That's why I kind of left the sd of x on the side. So what this is saying is if we look at the top, we have p of x greater than or equal to 50 is less than or equal to 1 over 15 squared. This is just 1 over 225. So in other words, what we have is, well, we have 1 billion transactions. So we have 10 to the 9 p of x greater than 50 is less than or equal to 10 to the 9 over 255, or roughly 4.4 million. So at most, 4.4 million transactions can be over $50. So what this means is if you're going through your transactions and you notice 7 or 8 million, then you're going to be like, something is wrong. So these inequalities are really here to kind of help you figure out, oh, am I doing everything okay? Is everything nice? Is it nice and easy? So it's kind of there for that. So yeah, so that's it for Chebychev. In the next next video, we're going to talk about the central limit theorem. So I will see you then.